Thank you very much, and thanks both Chris and Matt for bringing us together, and it's a very nice workshop, and I feel very embarrassed to talk again in front of the half of the audience that have heard this talk, and especially at the APS meeting, but Chris insisted.
We promised to ask different questions.
Yeah. I even exchanged few of the slides.
You're like the Bible. Every time I see a new presentation, I get a little more out of it.
Nice trial. But I guess there are few of the people in the audience that have not heard this, so you can freely use your laptops or whatever. If whenever you see familiar slides, there will be few of the slides new, and maybe I put a different emphasis on some of the statements on the basis of the feedback that I heard from the last presentation, the APS, and now discussion. So basically I will give a talk about two parts. One is indeed this old theorem from 2015 and a new version of 2018, and then I'll talk about something which I have done together with Veronica. And tomorrow, Veronica and Flavio, they will divide the talk into two halves and talk about some of the follow-up works. So let me just start with Outlook. And again, it's mostly structured as in the APS meeting. I will just briefly for this audience introduce a marginal problem and that part of the Bell's theorem that is really relevant for the no-go theorem. And no-go theorem will be no-go theorem of, facts, objective facts. Then, I will introduce with one slide Wigner's friend thought experiment and present the no-go theorem for what I call observer-independent facts. And one possible lesson from this observer-independent no-go theorem for observer-independent facts is that maybe indeed we should think about facts relative to an observer or to an agent. And that's basically where I stand. The outlook is actually development of my thoughts about that. And after this no-go theorem, I think still to a large extent, I think that facts are relative to observer. And that's a very nice position because it's a democratic position towards all observers. It's a very symmetric one. And it seems that although these facts are different for different observers, you cannot come up with any contradiction because once they start to talk to each other, they will agree upon the facts. And then, since in this no-go theorem and Frauchingen and Renner no-go theorem, you actually involve many agents. There is this kind of opposition from the cubist corner that, this is not a problem because if different agents have different statements, anyway, the statements are always personal, and you cannot draw any really serious contradiction out of that. And furthermore, if they start to talk to each other, as I said, they will agree upon the statements. But then it came to my mind that actually you can reduce the hurt of this no-go theorem into the physical situation that involves really a single agent, and there is an operational way for this single agent to actually compare statements or predictions that would be either conditional only on what happens in her laboratory, and I'm thinking here about the friend, or make predictions that are conditioned on not only the facts that happen in the laboratory, but also outside of laboratory, namely the facts that usually we assign to Wigner. And that we have a way to decide which of these two predictions will be preferred by the friend. And this is not in contradiction with the statement that the facts are still relative to observer. It's just, I think the lesson from that is that we should learn what are the facts relative to an observer, to the friend, and that we should extend them not only to the facts that really happen in the laboratory, but also extend them to the facts that happen outside the laboratory, because they can be learned or experienced by the friend. Okay, so the new thing that I will talk about is, I did talk about in the past, but not at the APS meeting, about the relation to the Frauchen-Greiner paper, and people always ask me about that. And then I moved to what I just explained as a challenging the idea of facts relative to observer. But I think the way of this challenge, what this challenge tells us is actually that the friend has an access both to the facts from her lab and the facts from Wigner's lab, and then in that way we should understand this. Facts should still be relative to observer, but we should extend them in this way, and then everything will be again fine. So let me start with the no-go theorem, and the way how I introduced this during the APS meeting and now is different than in both papers, and that's I should actually thank Richard Healy, who criticized both of these papers, or the main idea of that, or the way how it's proven, and helped me to understand the better way to argue in favor of the assumptions, what I try now to do. So here I start with the definition of the joint probabilities of 4 possible events that I enumerate by 2 bits. The first bit, z and x bit. And whenever the joint probability is defined, we can build out of the marginal probabilities. For example, if we are interested only if the event belongs to the blue or gray row, we sum up over the second bit. Whereas, believe me or not, this is red. If you ask whether the outcome belongs to the red or black column or yellow, here, at least on my screen, then we sum up over the second bit. Now, the marginal problem is actually the opposite problem. You are given the marginals and the 2 marginals, and then you ask yourself, is there a joint probability that returns the marginal probabilities? And in this very simple example, we can answer this affirmatively, but the Bell's theorem is actually the non-trivial case in which 2 observers measure marginals, and here again we have 2 possible measurement settings for Bob, ZB, XB, and for Alice, ZA and XA, and they can choose each one measurement setting and obtain the 4 possible marginal probabilities. Okay, and then the question is there a joint probability that returns the marginal probabilities in a way that I can really sum up over those variables that have not been directly observed, and can I get the marginal probabilities again as I have defined them, or they are given at the beginning. Okay, and now the important, and this is I think the important for the understanding of no-go theorem, is that if there is a measurement setup in which Alice can measure these 2 variables jointly, and Bob can measure his 2 variables jointly, then there, by definition, exists the joint probability, which is normalized and well-defined. And therefore, all Bell inequalities will be satisfied. And furthermore, these Bell inequalities will be satisfied independently of whether in an actual experiment, then we do measure them jointly, or we measure just marginal of them. So the mere fact that there is one single experimental arrangement in which we could measure and we can measure them jointly already implies that joint probabilities exist and the Bell inequalities will be satisfied. And then later on we can choose whether we measure them jointly or not. Okay. We also have the means through the Bell inequalities to prove no existence of joint probability. For example, this is the Clauser-Horn-Shimoni-Holt inequality. If we are, for this combination of probabilities larger than 3, then we know that there is no joint probabilities. Okay, that's all what I need from the formal point of view of basis for this no-go theorem. And then I also want to introduce something what I will call operational approach or minimal assumptions on the notion of quantum state and Heisenberg cut. So whenever I talk about quantum states, I will assume that these quantum states can be verified, in principle at least, by performing a suitable measurement. That's why I will not explicitly talk about quantum states of the universe, because I would like that whatever state I write down have some operational meaning. And this is a minimal requirement in a sense that you can assign any ontological meaning to the quantum state if you wish, but at least we should agree upon that they should give some, on the basis of quantum states, we can make predictions for future measurements. And the secondly is about the Heisenberg cut, which is here not understood as any physical distinction between microscopic particles, microscopic measurement apparatus, but rather a functional distinction, a distinction that is necessary to even talk about measurement results. It's a distinction between object and subject or system and observer. And it can be shifted arbitrarily far. So that's kind of an assumption of universality of quantum theory, that this Heisenberg shift can be shifted arbitrarily far to, from the system to the friend, to the Wigner. So in a sense, here we have a typical situation. We have a system, measurement apparatus, and friend. And obviously, there is somewhere here the cut between the system and the measurement apparatus for the friend. But again, for a different observer, Wigner, we can put this everything in a box and describe it unitarily. And describe it by a suitable quantum state that, again, has only meaning in the sense that Wigner can perform some measurement on this quantum state and verify maybe the state assignment.
So when you say verify,
no, it's not with certainty.
Is it crucial that you consider many verification tests?
It's not.
So for instance, if I say there's a true probability for something 50-50, can that be verified?
Sorry, if it is a 50-50, but you can do this way, but not in a single one, then I have to repeat measurements.
But you'd be willing to count a use of the law of large numbers, allowing you to say a probability one statement, and then you check yes. A frequency, for instance.
Yes, I would allow that.
And that would be a true verification. That would be a...
That will be a true verification.
Okay. I'm just anticipating that you're going to say that when I make a probability one statement and I have a look and I see it, then that verified not only the fact, it also verified the probability one statement.
Yes.
Yes. Okay.
So in moving the cut, the Friend's measurement instruments then loses its function as a quantum mechanical system, and as loses the measurement instrument will not be anymore a quantum mechanical system, but will become. Oh, I'm sorry. The measurement instruments will not be anymore an instrument or measurement apparatus, but will become a quantum system for the Wigner. And it could be observed by further measurement instruments by Wigner. Okay, and that's the usual setup, which we have seen now so many times in many different talks. There is a state assignment given by Wigner, where we assume that Wigner knows, for example, the initial state of the system and the friend state. The friend state is here modeled by 0. What I mean with this is a very particular degree of freedom of the memory of the friend. Of course, all the other degrees of freedom could be very mixed, and I think this also can be very mixed as long as there is two distinguishable classical outcomes. I see up and I see down, then I also think that you can create sufficiently coherence between these two situations. This is, of course, not impractical, but we are talking about a matter of principle. And then after a while, and after the measurement has been performed, we end up with a state of entangled state between the system and the friend. And it's something which we always do not specify often enough. But what it means is, of course, we can put here any phase which we like. We usually, as a theoreticians, just write this state like that. But implicitly, what is hidden here is that we know very precisely what is the initial state, and that we know very precisely what is the whole unitary or Hamiltonian of the system. And that's why we end up exactly with this state that has a very particular phase, and we take it this phase to be zero phase. But this already tells us that Wigner very well knows the entire dynamics and state assignment or state of the system in the box. And then what I want to say is that at the end he can maybe perform this measurement. Is the state exactly as in psi t, or it's not psi t? That's one type of measurements that I will actually consider in the next slides. On the other hand, we have a friend who assigned a state to the system, and we see that there is this different state assignment, and that's well, the beginning of the whole Wigner's friend paradoxical situation, because these state assignments seems to be of different nature, and then we think that this might even constitute a certain contradiction, but it's not obvious that we can end up with any contradiction, because if we want to compare the two state assignments, for example, Wigner by opening the box and comparing the system, and he will end up with one of these two situations, and they could talk to each other and actually agree upon state assignment after the measurement has been performed. So it's not obvious that there is a real any contradiction here. Okay, so now there is this very, I understood, a critical step with the Deutsch version of the experiment. I must explain why I like this, but at the same time why I don't think this is essential for the argument. So what Deutsch proposed for very different aim, namely to disregard Copenhagen interpretation in favor of multi-worlds, is that Friend can inform Wigner about seeing a definite outcome, and this message doesn't contain any information whatsoever about the actual result in the box. And so it, in a sense, if you write down, it factorizes out this message from the initial state assignment and can be sent out without revealing any information about the outcome seen, and also without influencing the state as seen by Wigner. And this message could be kept on the side of Wigner. Okay, so why I think this first a completely non-informative message, because whatever the message is, whatever the outcome is inside the box, the message is always the same. It was just for me very important because you can think about, well, I know quantum mechanics well enough. I also have experience in working in the lab. So I know that actually whenever I perform some measurement, I see a definite outcome. And you can stop there and go for the next stage. I was thinking like, okay, imagine this is the box, and basically maybe I don't even know where the quantum theory applies. Maybe I want even to make a statement that goes beyond quantum theory. And who knows what the experience of the friend is there? Is there any way that I, on the Wigner side, if I put myself in this role, is there any way that I get some confirmation that actually Friend performed a measurement and saw a definite outcome? And that's the way to do that. It's not essential for the no-go theorem. It's just the way to give some confirmation that indeed there was a measurement, to have some like direct evidence that Friend has observed a definite outcome, and at the same time Wigner is able to perform his own measurement. And that's the moment when you think, aha, maybe this is exactly the measurement scheme in which I can observe joint probabilities, because I see my outcome and Friend tells me I measured Z. I don't tell you which outcome I have seen, but I measured this. So it seems like, aha, this is from operational point of view, not going into quantum mechanics, not checking whether these two observables commute with each other. Just on observational level, it seems like this is a measurement setup that allows me to assign joint probabilities for these two measurement outcomes. Then I start to worry about that. Then I say, okay, that's good. I have some evidence that we both measure something. And maybe I'm tempted to conclude that this measurement arrangement really allows me to assign joint probabilities. Yes?
Are you willing to defend yourself against Matt's previous complaint about this?
I mean,
what was that? No, I mean,
I was kind of willing to let it slide because Caslav said it's not really important for the no-go theorem.
Oh.
This is just an intuition pump here. But I mean, my complaint against Deutsch is that it's based on the intuition that friend sees up evolves to friend sees up, I see a definite outcome, and friend sees down evolves into friend sees down, I see a definite outcome. And then by linearity, you say it applies to all states. But that's based on our intuition. You can also have the intuition that when the friends in a superposition, they don't see a definite outcome, which is an intuition many physicists would have. So you could say friend sees up plus friend sees down evolves into friend sees up plus friend sees down tensor, I don't see a definite outcome. Similarly for the minus state, and then you derive that for all states by linearity, the friend outputs that I don't see a definite outcome. Right? So you just have two conflicting intuitions here, and it's like, so the argument doesn't really do much to sort of resolve the tension of whether the friend does or doesn't see a definite outcome.
I basically now took this criticism into account. That's why I'm telling this in that way.
Oh, how are you telling it differently?
I'm telling this is non-important. It was important. I'm telling it's unimportant for the no-go theorem, and it was important for me to come up with a situation in which I can, in operational way, be able to argue there are good reasons to assume that in these situations I should assign joint probabilities. Once I do that, I'm in a trap of a hidden variable models, but there is a reason why I step into this trap, because there is a way that I see my outcome, and I'm sure that she saw an outcome. So it must be this experimental arrangement that enables us to assign joint probabilities. Okay. And then I can now appeal to the introductory slides about the Bell's theorem, saying that whenever there is one experimental arrangement in which I can assign joint probabilities, then in an actual, maybe future measurements, I don't need to measure them jointly. I can measure only marginals, but still these marginals can be obtained through the joint probabilities. And this will be dangerous step if I think about two copies of this situation, where I still assume the friends measuring, well, Z observable, and then Wigner's, for example, they can measure in the whole laboratories in this complementary basis, which I denote as X, and the friends can send out information always. I do see a definite outcome. That will be enough for me that for Wigner A and B they are tempted now to conclude that this is an experimental arrangement that allowed them to assign a joint probability, and therefore that all Bell inequalities are satisfied. Okay, so now I make a step to the assumptions of the no-go theorem, and then we will, of course, go into the relation of Bell inequalities. So the assumptions of no-go theorem is, well, some of them very similar to Renato's talk, universal validity of quantum theory. The quantum predictions hold even if the measured system is large enough to contain itself an experimental. Then something which I call observer-independent facts. There are different versions in different papers, but for this talk, it tells that there exists a joint probability such that different observers in their observations measure its marginals. Locality, the usual locality, the choice of measurement setting of one observer does not alter the measurement outcome of the other observer, and freedom of choice, that these choices of measurements are independent of the rest of the experiment. Okay, and now we go into the Bell test for Wigner and friends. We start with a particular state. This state is an entangled state between two systems, and the friends are in a stand-up state, like awaiting a measurement, and I slightly rotate one of the particles, just that for the reasons that actually both they measure z, and both measure x complementary basis. It's not so relevant. And then when I apply this rotation, I obtain this entangled state on the systems. And then at that point, friends perform measurements of the spin along z and allow to entangle actually all four systems, two systems and two friends. And this is just the same state written once more. And this is the coding, namely what I mean with this large phi plus and large psi minus is usually what we in a tangled basis describe as phi plus and psi minus. So this is kind of anti-correlations, and this is correlations, where these A up and B down, for example, or A down, are products of the spin and memory state of the corresponding friend. And the same is on the B side. Okay, and that's the final state, how it looks like, and the observables that will be measured on both sides are of that type, namely either the Wigners will ask the friend which outcome she has observed, so it's measurement of the spin along z direction if you want. Yeah, this will be basically open in the boxes, or they will measure the lab in the entangled basis, which corresponds to, well, spin along x if you think about the spin observables. And this measuring these two observables on each side will allow you basically to maximally violate the Bell inequality. And now you can look back to your assumptions and discuss which of them could be maybe relaxed. And if you don't believe in a universal relative quantum theory, this is a possibility, like a collapse model, G or RW, or D or G Penrose gravitationally induced collapse model. There is a locality which could be abundant, like non-local theories in the de Broglie-Bohmian mechanics, or even super-deterministic theories that do not satisfy freedom of choice, but I guess it's most interesting, really observer-independent facts. And I list here all possibilities, although I must also admit, just like Renato said in his APS, I think, talk, that it's not obvious how to even put many worlds interpretation in this framework. I guess there is a many worlds interpretation of a Bell's violation of Bell inequalities, and one should follow this line, but it's not obvious really. And I have been also talking to a few of them, and some of them will say observer-independent facts exist, and the other will say not exist, and I'm not sure, and I'm not a specialist in the interpretation. But the relative relational state of Carlo Rovelli, cubism, and something which I have called Neo-Copenhagen would agree on this bounding on observer-independent facts. Okay, then you can. Well, what are the then possibilities? Yes, please.
Can you say a bit more about why you need the locality and freedom of choice? Because the way you stated assumption 2 was that there's a joint probability distribution, and that's already enough to derive the development information.
Well, okay, that's true. Yes, that's true. That's true. I think this somehow incorporates both of them. And previously, I have something about statements about statements of each observers. But if you make a probabilistic one and you assume already existence of joint probabilities, I think you don't need. I think you don't need then locality. It's already so strong enough. Huh?
I think you need a reason for thinking that with Because
Okay, yeah.
The difference with what you're doing here is that the Bruckners are doing a choice of two different.
Yes, you can maybe assume that there is a joint probabilities, but depending still on which measurement, because the Wigner still has a choice between two. They will not measure all of them simultaneously. And but depending on the choice of one or the other observable, you can change these joint probabilities.
Yeah, so I think the difference is that you want to make all of the marginals that we're talking about actually observed marginals, and then you need a reason for saying that they have to come from the same joint probability.
I think if Alice and Bob, I mean the external Wigners A and B, if they would measure all observables jointly, then they will satisfy Bell inequalities. Nothing, locality is not an issue. But since they do not do that, but still choose between one and another setting, then the choice of the setting can influence the joint probabilities. All possible four measurements that come into the play will always be these ZA, ZB, XA, XB. But the probability distribution over them could change depending on what they choose to measure.
So in this situation, the friend on the inside of the box, so there's a choice between the friend performing the measurement?
No, friend is always performing the Z measurement. The two friends are always performing the same measurement. Okay? And these guys here can open the box and ask the friend, or they perform in entangled basis.
Okay, so the Wigners
choose between two measurement settings.
Have freedom of choice.
Yes.
The friend never has freedom of choice.
Never has freedom of choice. Yeah.
Remember that you said this.
Would you be able to get away with something that sounds a bit milder, that's just like when Wigner asks the friend what they saw, they get the right answer? Like if you're assuming that the ZA and ZB exists in every round, then maybe all you need is that when Wigner chooses to ask the friend.
Instead of locality, or you mean, or what?
Yeah. Or it's like, I mean, maybe it basically amounts to the same thing, but maybe there's a way of making it sound a bit more.
I think what's going on is that, Caslav would like to get the conclusion for actually observed probabilities, right? So, the problem in the version that I presented is that there's nobody who observes all those probabilities. So here,
yes,
Caslav is talking about the actual statistics that Wigner obtains in each of these four experiments, the actually observed statistics. And he would like to use those to get to a contradiction. And because now you have a situation like in the standard Bell inequality where there are counterfactual choices. And so you have to have a reason for saying that the probabilities are the same in all of those experiments.
And this is ensured by a locality. And I think you have to take this, that they can choose settings if you want to show violation of these inequalities.
If you want to actually show it if you want to be able to write a Nature paper which shows a violation.
A violation, you have to do it. But this, then you open the possibility that by choice of measurement setting, you really influence the joint probabilities. Whereas if they fix the setting and measure all four of them, you will assign joint probability. I mean, nothing speaks against, let's say. Yeah. I don't know how operationally you will prove that. Okay, so...
But there is an asymmetry here. Not that it's relevant for the discussion that you guys are making, but you have a built-in asymmetry in that friend has no freedom of choice. The friends have no freedom of choice. The Wigners do.
I mean, in that setup is important that Wigners has a freedom of choice. I mean...
Oh, I understand. It's crucial for what you want to prove.
Yeah, I don't know whether
But what principle tells us when an agent has freedom of choice and when an agent doesn't. You see where I'm going.
Workshop.
No, it's this one. But this is the first instance where you use it.
Okay.
You're going to use it again.
I mean, this is now a continuation of our lunch discussion. I would say what is important for this no-go theorem is that that even if you assume that there is a free choice by the friends, the Wigners can still describe that in a unitary fashion. That will already allow them to know in which basis they should measure in the Bell's theorem test.
I'll let you go.
Thank you. Okay. Good. Okay. So what can you? What is the message out of this theorem? So one is that I will end is that there is a relative facts relative to observers. The other one is maybe to say, only the facts of one of them are real in some sense. I don't even know what it means, but anyway, this is a dead end. And for example, Wigner facts are more fundamental because he has a better instruments and better control. But again, you can think about a hierarchy of Wigners in which you can relativize these facts, Wigner's 1 facts or Wigner's 2 facts, because you can have a series of Wigners. And therefore, there is no absolute facts for any of them. So you soon get into indefinite regression of observers. As I said, I'm not sure what is really the way out. I mean, how the many worlds will describe this, but I guess you can go up to the wave function of the universe and say these are actually the facts. The other possibility, which is more appealing for me, is that there are no facts of the world per se, but only relative to observers. The argument could be also made deterministic. I didn't pay attention on that. I mean, I just mentioned this. You can go into the 3 Wigners and 3 friends and do basically the GH set state with appropriate assignment of the observers for the friend and for the Wigner, and you will end up with the same conclusion. In which case, maybe you think that you can adapt observation independent facts from the statement that we have there exists a joint probability such that different observers in their observations measure its marginals to something which is more about truth values of the statements, so that one can jointly assign truth values to the statements about observed outcomes of different observers. In other words, that they build a single Boolean algebra. I think Jeff will talk more about maybe along these lines. I'm not sure, but I saw in the abstract. And also, I want to acknowledge the fact that we heard already today. Well, I don't know whether it's the same what you show.
Yes.
But okay, exactly. So in 2006 already. Schack and Caves talk about the facts that are facts for the agent and not the facts for everybody. And I see this no-go theorem in some kind of a support of their view.
Correct. It's not Schack and Caves talking. It's Fuchs talking.
Okay. Two Schack. Yes. Oh, sorry. Yes, you talking to them. Yeah. Sorry.
So they were very stubborn. They didn't like the idea.
They didn't like.
I agree. Yeah. I changed my mind.
And you can too.
I only arrived now. Okay. So
no, this does provide support. I agree. Your considerations here. Where we disagree is somewhere else.
Yeah, there is enough room still. Especially in the second part, I guess we will disagree. I don't know how much time do I have.
Well, you started at
like
first.
You're the last person who can talk forever.
I talk forever.
Yes. Go at least
50? 15?
At least 15 if you want to leave 15 for questions.
Oh no. Okay, so let me briefly comment on the relation to Frauching and Renner paper. I repeat the axioms of this paper from the second version. It's a University of Quantum Theory that is very similar to what we had before, except that here is enough to restrict yourself on the assignments of probability 1 or 0, because it's a deterministic argument. Then there is a consistency argument, or assumption, which tells in the sense that the different agents' predictions are not contradictory, and something which we call single world, that from the viewpoint of an agent who carries out a particular measurement, this measurement has one single outcome. I must say that I never fully understood this one, because the one who carries out a particular measurement, for him there is only one outcome. Maybe for somebody else, but yeah.
Now I understand it better. It just really means that if you use the other two rules, you should not at the end come to contradictory conclusions. I think that's what it means. So it shouldn't be that you use Q and C and know the outcome is 1, and actually you see the outcome 0. But it's true that only became clear. So that was one reason why I now think it also applies to many words, because in the original formulation, many words wouldn't have been affected by that. Whereas now in this formulation, you could say if you apply it to one branch, then you see that it may be problematic for many words, which then turns out to be true. Yes, but you're right. I mean, the formulation in the paper was indeed not optimal, and I think I made progress in understanding how one should phrase it.
Okay. So the argument basically combines a set of statements, and I mean, I guess most of you are already familiar with this, which I called S1 to S4 statements, and statements by different observers, friend 1, 2, A, and W. And there are these 4 statements that I like actually to read in inverse order. Brukner sees OK, and it's told by A that X is OK, and then you jump into the next one. Oh, if A sees X OK, which was here, then F2 sees Z plus, then you jump here. If F2 sees Z plus, then F1 sees R is T, and if F1 sees R is T, then V sees W is not OK, which is a contradiction with the beginning here. And this is now what we have already discussed. There is a slight difference between the status of these different statements, because only the last one is really observed by performing an experiment. By Brukner, the others are not directly observed, so you put yourself somehow in the role of the other observers and apply quantum theory, and then you come up to these statements. And what actually this consistency assumption, how it works for you, well, we have exchanged so many emails, Renato and myself, but it's one of them, he uses wording like collapse others' knowledge into one's own knowledge. So that the statement that you will like to make is that V knows, that A knows, that F2 knows, that F1 knows, that V is not OK, actually implies that V knows that, V is not OK. And then you compare this with this statement. And that's what brings you into the contradiction. So this is an assumption about how you can use other people's knowledge. And it's a much weaker assumption than assumption of existence of objective facts. But at the end, it has a power to arrive at the same conclusion as if you would have this stronger assumption, and that's the relation between two papers, as I understand that the stronger assumption is really the assumption that propositions of different observers build a Boolean algebra and can be jointly determined. And if these objective facts would be true, then all these statements can be compared in a logical way, and then you can really combine them, and you say, well, P is true, and then you take this and P implies Q, and Q implies R, and R implies not S, which is not S, and then you can compare with the previous statement that was part of the fourth statement that V is OK, and you come up with a conclusion, with the contradiction, sorry. Now, the question is violation of consistency a problem or not? And there is this nice example by Sudbury, but I think many people came up with the same idea that and it was also by Matt mentioned, that you can have some, for example, in the relativity, statements that seem to be contradictory statements by different observers, like every inertial observer claims that his clock ticks faster than that of a moving partner. But we resolve this, and we don't think that this is a problem for a theory, because these statements have only meaning with respect to the specific observer-dependent measurement procedure defining simultaneity. And here, the situation is even more severe in the sense that we don't really have a manifolds in which we define the events in an observer-independent way, but has also some kind of similarity in my view, because the quantum states refer to outcomes of different observers in Wigner-Friend type of experiment, and they have only meaning with respect to observer-specific experimental arrangement. And this is very much in a line of the Bohr's idea of complementarity. So that, again, we have a different measurement procedures when we assign different states, as they do like Wigner's friend and Wigner. Of course, we would like to understand it better, and as I really acknowledge this as an important task for all of us to get some clarification when we can use other agents' knowledge for our own inference and when we cannot do that. Because obviously in situations which we don't have a Wigner-Friend situation, like when we do not, let's say, measure memory of friend, we can exchange information and knowledge and use it as our part of our own knowledge. So there is still something to be done. Okay, now I would like to challenge the idea of facts relative to observers. And I think there is this experimental situation which really put a serious question on that. And it, at the end, involves only one agent. Of course, there are different levels of description of this agent, but at the end, this one agent will make predictions, and this one agent will then face the consequences of this prediction and can make some evaluation of his previous prediction. And here is just to remind you on the standard state update rule that we use in our labs, that whenever we have some facts in the lab, like a measurement result, that we accordingly update our knowledge such that in ideal case we say the state after I have observed the last outcome corresponds and is represented by this, bracket psi for all future measurements. And this is operationally justified. When we repeat the measurement, we can confirm that this is the state. And I think there is no doubt that in all our experiments, this has been confirmed. Okay, now I introduce the game. And the game is the following. I have a friend. She performs a measurement. Now I assume that there are d possible outcomes, because I will want to make the largest possible discrepancy between friend's prediction and the actual statistics. So I will let d goes to infinity at some point. And now Wigner, who describes the whole unitarily, end up with the description of entangled state between system being in state I and friend seeing this outcome I. Now, at the beginning, I assumed the very natural assumption that indeed applies for us in laboratory. We don't know in which state we are, or this maybe even doesn't make sense as maybe others will state this, but only knows what has been observed in the lab. That's the only fact. And she will condition on this fact. And then she's also told that Wigner will perform the measurement of the type of this verification. Are you in this state, or you are not in that state? And then she's required to send out towards Wigner her prediction about this future measurement. Now, Chris will jump. Okay?
He was trying to block me.
Yeah, no,
I saw
no.
the hand come out.
Yeah, can block him, please. No. So now, what will be a friend's prediction about this future experiment? Well, you can say I don't want to make this prediction because this involves also a state of myself, and as a quantum Bayesianist, I deny that this is a meaningful question. This example is not about that, so I allow this path as well. So you can say I'm not interested in that at all. Okay? Or you can say, well, there is maybe no problem in assigning to myself a state. And I think very often in normal classical situation, or even in situations when we deal with the quantum experiments, but we are not Wigner's friends, we do that. There is no problem in saying the system is spin up, and I'm aware that the spin is up. You can even, the whole Born rule, you can say, if I'm aware that the spin is up at t0, what is the probability that I will be aware that the spin is x at some later time? I think if we do use this language, it's equivalent as the language about the systems, as long as we are not put in this situation. And that's why I do here allow friend even to assign the state to herself to make a prediction about this future experiment. And since this overlap is 1 over d and d goes to infinity, the friend will predict that it's highly unlikely that she will end up in this state if she conditions on the experience in the laboratory. So she can send out this prediction. And now it's important that this prediction doesn't reveal any information about which outcome has been observed. So no matter which outcome has been observed, this prediction will be always the same. So it factors out and can be sent out without the change of the state itself, and can wait outside to be compared later on by whom? By the friend herself. So now I will explain how. Now, it's done for the Wigner to measure the state. And this is, since system and friend are actually in the eigenstate of the measured observable, this measurement or projection of this psi will not change the state. And furthermore, this measurement will give result 1 with certainty. Okay, once Wigner can then tick, it's result 1, not 2. And then they can run the experiment once more. And once more, friend will give prediction, and the prediction will be the same. And then Wigner will tick once more, 1, 1, 1. Okay, and after a while, if they think, or if Wigner thinks, or machine thinks, if this is a machine programmed by friend beforehand, that the statistics is sufficient, they can stop the experiment and Wigner can open the box. And of course, in this open the box, the friend will collapse into one of those results, but it's not so important because there are already 2 evidences that her previous prediction doesn't quite match the actual statistics. So when I was exchanging emails with Jeff, he actually proposed a different way of doing this, of coming up with the same conclusion. This is alternative way, in which actually friend never leaves the box. So the friend just writes down always prediction and keep in the box. The Wigner can perform the measurements, doesn't change the state of the friend and the system, and after sufficient statistic, or even after each individual run, sends this information into the box. So now the friend can compare this without ever leaving the box, the 2 lists. What is important to me is that no matter which way they choose, a friend is likely to eventually update her state assignment, or I think there is sufficient evidences that she can do better, if you want. Okay, so I was aware of that for some time, and I was for quite a while of opinion that this really puts the idea of facts relative to observers into question, and suggests that, well, she can convince herself that following the usual rules of quantum mechanics, she fails to make a correct prediction, or there is a big discrepancy between the actual statistics and her prediction. And therefore, that maybe, in certain sense, Wigner facts are more important than Franz facts. And this is not nice, because it breaks this symmetry that was so nicely somehow established through the no-go theorem. But now I think that the way out is that we should think of facts for the friend as a combination, not only about all information that is in principle available in the lab, which are measurement results, but also facts that are available to Wigner. For example, how the state is prepared, the Hamiltonian describes the measurements, for the simple reason that actually Wigner can send this full description into the box. And this could be another fact for the friend, freely available. There is nothing that will change the state description of the friend, that will change. It will just extend friend's knowledge with the facts that are anyway available. And therefore, then, having this state, the friend, and this is like slowly going into a more speculative part, because it's not something which we only recently think about that. I mean, this is a part done together with Veronica. That friend might maybe use two states in this very simple case. Two states, the one that is conditioned only on the results obtained in the laboratory, and the other which is conditioned on, well, if you want, results obtained in Wigner's laboratory. And depending on whether the friend makes a measurement on the system alone, or is told that there will be a measurement made on the system plus friend's memory, will take into account one or the other state. Okay, the very last slide is something where basically I stop and then Veronica will continue tomorrow. The alternative way, which I think is something along the lines what Renato was asking for, is kind of a framework or formalism that will allow the friend to make predictions without dividing this into different states, without necessarily knowing whether the measurement will be performed only on the system alone or on the system plus her memory. And that's the generalized Bond rule that was, I think, published last year or something, I don't know when, or came up on the quant page by Veronica and Stefan Wolf, which allows you basically to make that type of predictions, like if the result K was observed in the box, what is the probability to obtain entangled state when we measure the whole box? Outcome.
Probability of the state.
No, I mean, the state is assigned to a certain outcome. It's identification of that, but it's an outcome, correct. So when this paper came out, I didn't like it. I didn't like it because I was concerned with operational meaning of these probabilities. Again, the same objection as cubists is that there is an outcome of one agent and there is an outcome of the other agent. How they can ever test this statistical prediction, and is there any way to have a list statistic that will correspond to these probabilities? And so it was like, okay, you combine probabilities between two agents, but since there is no space-time point in which you can bring the evidences of the two outcomes, nobody can really write down these statistics. Whereas now I think that exactly the second part of this talk, or the way, show you in an operational way how you can measure these probabilities. This procedure actually provides an operational way for the friend to verify this prediction, either by sitting all the time in the box, as Jeff suggested, or going outside of the box. And I like the paper. And I think it's there hidden this maybe consistent way to deal with this situation and a condensed way that allows friends to do this type of predictions even if you have a series of encapsulated observers. So I come up with the conclusions now at the end. The first part was a no-go theorem, which is saying that it's impossible to jointly respect universal validity of quantum theory, the observer-independent facts, locality, and the freedom of choice assumption. And the second one, which suggests that Wigner's friend is actually entitled, there is nothing wrong in that, to use both the outside and inside perspective, and we can still then think about facts relative to observers, but we should understand what are these facts. And I'm suggesting here that for the friends, these are also Wigner's facts. Or alternatively, use the generalized-born rule instead of using 2 states or 3 states or n states depending how large is the hierarchy of the observers. And with this, I would like to thank you for your attention.
Organizes prerogative.
Would you go back to the slide where you first talk about this experiment?
First talk about that.
Yeah, at the very beginning. Oh, even before.
Even before.
Yeah. All I want to see is that equation. Stop. Right there.
Yeah?
Okay. No, I want this one.
You want this one?
I want this one. So we have the situation where the friend is in the box, and Wigner, by whatever means, writes down this joint quantum state for the inside of the box. What you next contemplate is that Wigner performs the measurement. Are you this state or not? Right?
Yes.
So, nothing wrong with that. Could Wigner contemplate performing a different measurement than that?
Wigner himself.
Yes, so I'm going to modify. I'm just going to modify
Not
the
to measure
expression.
this one.
Yeah.
Not this.
Could he measure a different basis?
Yes. Yes.
Does Wigner have the free choice to measure the one you consider or a different basis?
Yes.
Okay. I told you to hold on to this idea. Okay, so you contend that Wigner has freedom of choice for his measuring.
Yes. And why does the friend?
Okay. Now next, let us say the friend in the box. Wigner is assuming, because he's written down the state, Wigner is assuming that the friend will measure the standard basis. But what if the friend chooses to measure the Fourier transform basis? A mutually unbiased basis.
He assumes, I mean, if you...
So now, let me go one more step first.
Yeah.
So suppose the friend on the inside of the box rotates her Stern-Gerlach device. So, and she measures a different basis. Now she predicts that when Wigner performs his measurement, he will not get the one outcome with certainty. He'll get it with some other probability.
Mm-hmm.
Who's correct now?
Who's correct now?
Yeah, she makes a prediction that he will not necessarily get yes as the answer.
There are 2 variants of this experiment. That's why I wasn't sure what you are asking at the end. There is a very deep question, which I'm not on.
Can the Wigner do state homography?
and reconstruct it with many different mechanisms.
Well, he would say, yes, you can make a tomography, but can you make a tomography of her free will? That's the question.
You have an assumed asymmetry, and I'm wondering why you
What I
have...
want to say, that if you stick to the unitarity of quantum theory, then even the appearance of the free will of the friend should be able to describe in a unitary way by Brukner. All what Brukner needs is whatever friend does to describe this in a unitary way, know very well Hamiltonian, that would mean free will for friend, and know very well the initial state. Once he has this, can always then find such a state, for example, in which the outcome will be probability 1. Of course, doesn't need to choose this, can also choose the other one. So I think your question is very deep, and whether this is possible, and to me it suggests that if you don't allow me that, then we have to think of what it means, universal validity of quantum theory, and shall we stick to this unitarity? I'm just saying I believe in that, and therefore your free will is nothing else but another unitary for me.
Okay, so let me try to rephrase what I think you just said. We started off with you agreeing that Brukner had the free will to perform whichever measurement he wishes. But the friend actually has no free will. If she thinks she has free will, it is
Everybody
illusory.
thinks that he has a free will. Maybe there is a winner one.
And so Brukner out here, his free will is likely illusory as well.
I think if you stick to the unitarity extension of quantum theory, you have to admit it. I'm not saying this is as it
So
maybe real.
just to clarify, so that means that the friend thinks she has free will, even though she doesn't? Am I understanding that correct?
I think if you want still to say that every measurement procedure, including the choice of which measurement to be from, can be modeled by a unitary transformation, then you can maybe say it's just apparent free will for the person who performs the measurement. And for high level of observer, it's a unitary. Then Brukner also thinks, I think I have a free will, but then there's a Brukner 1, Brukner 2, and so on.
I see what you're saying.
I don't understand the relevance of this discussion about free will at all. Isn't the situation rather that these two guys, the friend and Brukner, get together before the experiment and they say, let's do the following experiment. You go in the box and you measure such and such. I'll stand outside the box and then we do this business. Now, I mean, so of course, if the friend agrees, then the friend's going to be in the box and do one thing. It doesn't, I mean, the question of free
I
will.
think he wants to challenge this and say, oh, this is a very special case, I come in and I do not do what you
Yeah, but then
See,
you're
but notice
changing the rules of the
that
game.
Caslav wants to declare one point of view correct and the other point of view incorrect. The friends inside the box is incorrect.
I think it's incorrect. There is an evidence
And
for himself,
that only
himself.
follows if you demand that the friend follow the protocol, which is what you're demanding. That they've agreed to it, and now they're both going to follow the protocol.
So what would you react then? Okay, let's
But the cheating is
stick to this one
irrelevant.
possibility. Do you agree that friend is wrong?
Whatever friend does, it's,
Let's just take this very special case. Friend does exactly they agree upon, and what is the consequence now for you?
Also, the friend has free will because the friend, while they're discussing, the friend can say, you know what, I don't feel like measuring Z. I'd like to make up my own mind. And then Brukner can say, well, what do you want to measure? The friend says, I want to measure in the X direction.
Yeah.
Well, now if the friend cheats, then of course the whole game is over. But
Well, the friend
there's
cheats,
no real-
and then which one is wrong? Caslav is declaring one wrong and one
No,
right.
if the friend cheats, then nothing follows.
The friend has to have the freedom to cheat, otherwise the friend has no reason to apply the formalism of quantum theory in the first place. If the friend only has one possible orientation of Stern-Gerlach, then there is nothing mysterious, there's no need to invoke the quantum.
No, that's just
All the friend has
absolutely.
all the friend has is
A single measurement of Stern-Gerlach device is not.
Sorry, the situation is very similar as in the lab. We have previous preparation. This measurement Z is just preparation for the friend. There is all set of measurements that a beginner can perform, and that's a usual situation of observer. I have a preparation condition on that. I have all possible measurements that I need to assign probabilities. That's what we ask for the friend to do. And then we see that the friend will be very weak in her predictions if she conditions only on the result in her laboratory. It's not that she does, there is a huge free will that of all of them to measure future measurements. Which type of the future measurement they will choose. So I don't think that this should be an answer of Cubist.
One of the things that occurred to me is that if you're taking the nested Wigner's friends all the way out, right? Then none of them have free will, right?
on the assumption that unitaries are ontic, etc.
But somehow I agree with Jeff that this is going into. I think this is a really interesting discussion, but it's not. I don't believe that Cubist answered on this should be. Let's consider this very restricted setup, and I would like to know whether you think that facts should be conditioned only in the lab or not. Is there any tension that you see here?
Yeah, I mean, I'd like to tie this again to my coffee betting example.
This is the answer I would give.
I don't see any trouble with no conflict between Wigner's description of the whole box as unitary, etc., and the friend's free will. One's is Wigner's perspective, his predictions, perfectly applying quantum mechanics. It's a very different matter for the friend when the friend tries to adopt Wigner's viewpoint. The friend is actually effectively making predictions about, well, what she is going to do. And that just doesn't work, because the friend actually has the freedom to make anything happen. So there is no.
Why doesn't it work? It works. If she
it's like
that's
me.
what Lydia said, but she doesn't have freedom. Lydia just said that, but she doesn't have freedom.
It's not the coffee analogy. It's like you always have milk in your coffee, and Chris knows this.
And actually, she doesn't have freedom of choice for the measurement setting.
Why not?
But there's still an outcome that has to happen that is not tied to her choice. That's quantum mechanics.
But why is she? In what way is she bound by Wigner's description and
she's not
unitary?
bound. This is a possibility that somebody can tell her, "Hey, you are in this state. Why shouldn't you use this knowledge?"
But now she's gambling on this, and so she can make any outcome happen.
But look, the
just doesn't make sense.
the gamble isn't the friend. It's nature that's doing the gambling. All the friend does is the friend sets the apparatus
From
up,
Wigner's perspective,
and nature
yes.
then, from inside the box, and nature makes a choice.
Okay, but
For
this
the
is-
friend, from outside, that's not the situation at all. So it's not like, I mean, the friend is an automata. The choice is made by nature here. Put it this way: your coffee example. If you want to make an analogy, the thing that's like the choice of coffee is nature choosing spin up or down. That's the connection with your coffee. So it's really the complaint you have is nature's free to choose up or down. That's the relevant freedom of choice.
That's where we differ. Because I'd say from Wigner's perspective, that's exactly how Wigner would describe this. I mean, this is Wigner's gamble, and it is basically what nature.
But Wigner, from Wigner's point of view, nature hasn't made a choice. It's the state is just a unitary transformation. You know, it's just.
Well, but Wigner could make the measurement and then force the choice.
Let's modify the experiment this way. Let's suppose that Wigner programs a giant robot. Okay, the giant robot is going to go inside the box and do this particular measurement that he describes with this particular interaction, and then the friend is constrained to be inside this robot. Friend can't move, right? Friends can still see through their eyes what's happening. Okay, so in this situation, the friend really does have no free will, but it's still there to observe what's going to happen. Now, we can ask Caslav's question again. Which of those predictions is correct? And now there's no possibility for the friend to do something else. So what will you say in that case?
Well, there wouldn't be any predictions. I mean, the friend is just
that's not quantum mechanics, though.
Sure.
Well, so if that's just knowing what the machine does.
Well, let's put it in a different perspective. Suppose the machine is actually a beam splitter, right? And you're pumping single photons through your beam splitter, and you only have a 70-30 beam splitter. That's all you have, right? And some come out this way, some come out that way. You don't have a choice of which beam splitter you use, but you still, that result is still quantum mechanical.
It's Malus law, but it doesn't require the full apparatus of quantum theory.
To put it in a different way, if it's a Stern-Gerlach device, it does. A Stern-Gerlach device, without rotating it at all, has two outputs that are not predicted by classical physics.
So I think actually
be a lambda.
Okay, so the friend is making a measurement. We have sort of, that's part of the rhetoric here, right? Now, isn't it part of making a measurement that it's legitimate to make as many copies of the result as I please? I mean, you're using a very, very specific state here, right? And including the exact way whatever record is made is actually encoded in a coherent way. So, in some sense, this is not the friend is not really making a measurement, right? He's completely bound by this one unitary operation that was pre-designed, and it's very far from what I would actually call a measurement. And so you
mean at that stage, right?
Yeah, that stage there, right? So there would be different ways of doing this. There could be many copies of what she sees.
I think this
and
is
so
all
on.
copies. This is all described here. Like whatever you do, this is.
Sure. You could put a lot of stuff in there, but it would be completely fixed and in this very coherent way that you've written there, right? So not much of a measurement actually that happened here. It's a coherent automaton that runs for one step. Okay, fine. But
I mean, when we make predictions about future measurements, we are not, using enormous intelligence. Like we hear the click or the last click, and then apply the Born rule and do that. And all what I want to say is that if friend does in a usual sense, it won't work, and there is no reason not to allow friend to use the Wigner's description, because this will give a good prediction. So I don't know whether this is quantum theory or it's not quantum theory. It just works, and for me it's sufficient then to use this in this situation, to use this rule. And it's not in contradiction with the idea of facts relative to observer. So I don't really understand where should there be a problem for quantum realism, because you have your experience. It could be a click, or it could be somebody tells you something, or this also, Wigner can send this state and it should click if it needs to click. It's just another experience, and all experience friends should take into account to make the best prediction she can.
Any further questions or comments from the audience? Really, everybody's satisfied?
No. My only comment would be 20 go to 10. So I don't see it.
Okay. All right.